Hi, this is the second video in a series on LCDs and how to drive them. I'll link in the first video down below which talks about LCD technology and how they work and things like that. This one we're going to look at driving a static LCD, i.e. a non-multiplexed LCD. Let's get to it. So we saw in the previous video that an LCD is just constructed with what's called a common, which is actually more technically called the backplane electrode in there, and then just basically the segment pins, however many segments you've got. And this is your typical static LCD will only have one common on here. So your LCD display is a glass sandwich with some liquid crystals in there, and it'll have at least one common pin or COM pin, which is actually more technically referred to as the backplane electrode. And then you've got all your other pins which drive your individual segments. In this case, we've got a classic 7-segment display with one COM, and that's what we use in the practical example coming up. So how do we drive this thing? How easy is it? Well, it could, in theory, be as easy as this. We'll take a look at two different ways to drive it. One of them's correct and one of them's incorrect, but still kind of sort of works, but you don't want to do it. So, trap for young players coming up. How do we drive it? Well, if we hook our common pin up just to our 0 volt, our ground pin, and we can simply drive, put 5 volts on any one of the other pins. A typical LCD driving voltage might be 3 volts to 5 volts, something like that. And we can actually turn these segments off and on just with a digital signal. You can drive it with any sort of digital logic, microcontroller, or anything like that. And it will technically work, as I'll demonstrate shortly. But this is actually an incorrect way to do it. You do not want to drive this. Why? Because, well, let's assume that you have 1 second on, 1 second off, a 50% duty cycle. It's going to give you an DC average voltage of, in this particular case with a 5 volt drive signal, 2.5 volts if it went up like that, for example, when it was 50% duty cycle. And DC offsets on an LCD will eventually kill them. You do not want to use this method to drive your LCD, but it does technically work. Now, some people will try and get around this by driving it with a burst. In this case, you know, you could have, say, 100 hertz or something like that to try and get your DC average value lower. But yeah, it's going to lower it, but you're still going to end up with some DC level on there, and it's not going to really eliminate the problem. Now, you can actually kind of use this method to actually drive it correctly, but you've actually got to take this negative for an equal amount like this, and in this case you do it as a burst like that. So you've got, say, you know, that can be your 100 hertz burst, for example, just, you know, a low frequency, and then on and off, and then your DC level, instead of being 2.5 volts, your DC level, average DC level, becomes 0 volts. So this will be the correct way to drive your LCD using this. But the problem is you've got to have a negative 5 volt rail down here, and that's going to ruin your day if you've just got your digital logic, your 3.3 volt digital logic, 5 volts, you've got an Arduino to drive it, some other microcontroller and you just want to drive your LCD. Getting that minus 5 volts is a pain in the butt. Anyway, let's go have a little play around with this on the bench, and then we'll come back and show you a more elegant solution to solve this problem that doesn't use a negative rail.
Not as clumsy or random as a blaster. An elegant weapon for a more civilized age.
So let's use the example of this same 7-segment LCD that we used in the previous video. I'll link in the datasheet down below. It's a nominal 5 volt drive static display, which means it only has the one common pin, which is down in the bottom left corner there, and we're just driving one of the segments here, 2 volts per division with a 5 volt TTL signal there, 1 hertz on, off, on, off, on, off, simple like that, and our ground reference point is there. And as you can see, that works just beautifully. That segment's turning off and on. The contrast is beautiful. Couldn't ask for anything better. You might hook this up to your microcontroller and think, hey, I can just drive this with my 5 volt TTL signal or my 3 volt TTL signal. This one will also work down to 3.3 volts in this particular case. And you might think everything's hunky-dory. You might design your product around this, and it might work for 6 months. But look at the average DC value, of course, because our ground reference is here. The average value is up here like this at 2.5 volts. I mean, I could just leave this at 5 volts, hook up the pin just permanently at 5 volts. Yeah, the segment will come on, but then your average DC value relative to your COM pin is 5 volts, and that's going to eventually kill your LCD. So while this might work, in quote marks, do not drive your LCDs like this. You want and need a 0 volt average value for your drive signal. 100 hertz continuous, 100 hertz square wave. And as you can see, the segment is on, but the contrast isn't that great. Now let's have a look what happens if we actually adjust the DC offset of this signal. So let's actually shift this down like this, and you can see that if we actually take that to 0 DC offset, so we've got plus minus 2.5 volts, still 5 volts peak to peak, you'll see that it's actually vanished like that. So the nominal 5 volt drive for this particular LCD isn't good enough. Now if we actually continue to take that down to negative, you'll actually see that come good again. So that's just the difference that the DC offset can make to the contrast on an LCD. You can see that our signal drive level is still exactly the same peak to peak, but it's just not good enough. And it doesn't really matter what you do here. When you've got a ground reference here and you're just driving your LCD positive, in this case I've got a 0.5 second period, so it's flashing at a 2 hertz rate every 0.5 seconds, and I've got a burst of 100 hertz frequency in there. You're still going to end up with an average value which is, well, it's not going to be in the middle anymore, but it's still going to be somewhere above 0, and that's eventually going to damage your LCD. So there's just no way to drive this with your 3.3 volt or 5 volt LCD signal directly as you know it, like your regular 0 to 3 or 0 to 5 volts. So let me take it up to 8 volts here, for example. The amp, like it's coming on nice and dark, but you'll see it never switches off. Why? Because look, our DC, our minimum level here is at minus 4 volts there. It should be at 0. We need to drive it both positive and negative with the average value of 0, because the average value at the moment, look, is minus 2 volts. It's not actually 0. So if we actually shift our DC level to ground here, and this is the correct way to drive it, a solid off and on, which we could achieve by other methods, but this way, there's no DC offset on the LCD, we can't damage it. So we've got to go both positive and negative, but that is a real pain when you're using digital logic to drive this LCD. So whilst you can get away with using this method number 1 here to drive your LCD, it requires that negative supply and to get your DC average at 0. So it's not a very practical way to do it, especially with digital logic. So we're going to have a look at another method. We'll just call it driving the COM pin, driving the common pin. And this is basically the more industry standard way to do it. It's how most of your LCD driving chipsets, be they static ones or your multiplexed ones, which we'll have to do another video on because it's more complex, actually work. So instead of actually hooking our COM pin up to ground here, we're going to actually drive the COM pin with a digital signal like this. And this is just your regular digital signal, let's say 0 volts and 5 volts like this. We're driving that backplane electrode in there. And you might think, why? Well, stick with me. It gives you a nice little trick you can do to avoid this negative 5 volt rail up here. Now you might get a little bit confused by the terminology, that industry terminology of COM. Common, you might think common's always ground. Well, it doesn't have to be. The LCD is just its own independent floating thing. This LCD here doesn't care what this pin is hooked up to. It can be hooked up to your circuit common, your 5 volt rail, 1000 volt rail, negative 1000 volts. It doesn't matter. It's only the relative difference between the common pin and the segment pins up here that actually matters to the LCD. So we can drive that common pin with, let's say, 100 Hertz might be a typical driving frequency. It's high enough frequency to avoid any visual flicker, but it's low enough not to chew a large amount of power due to driving the capacitance. The higher frequency you drive your LCD, the more you've got to drive the capacitance, the more reactive current that you're actually going to get through the capacitance of the LCD, and the higher the power consumption. That's why your LCD watch can last for years, assuming you don't have one of these newfangled, stupid, idiotic smartwatches, can last for years or 10 years, or the shelf life of the battery is because the LCDs take practically nothing because they're only switching at 100 Hertz or something like that. So if we're driving the common pin with that 100 Hertz, what does that achieve? Well, it achieves a neat trick in being able to avoid the 5-volt rail. Let me show you how. How do we turn the segments off and on? Well, you could leave the segments off just by having these pins floating, of course. A tri-state output on your driver, for example, then in theory, your segments would stay off because there's no voltage difference between those. The pins are just floating. But because, as you saw in the previous video, how just the electric field picked up by my body, I could touch the pins and cause those segments to turn on and stay on due to their capacitive charge and things like that. You don't just want to leave these pins open because they could eventually build up charge on them and then turn on, actually drift on. That you always want to drive them. So in this case, if you wanted them off, you could simply just tie them all like that. No problems whatsoever. If they're all at the same level, there's no difference between the common pin and the segment pins, and the segments will stay off. No worries. But let's say you wanted to drive segment A here. How do you do it? Wow, it's easy. You use an invert. You'll notice that we don't have an inverter down here. It's just a driving gate. But if we hook an inverter up there and the same 100 Hertz signal here, but we invert the phase, let's take a look at the resultant waveform. So if we draw two separate waveforms of the waveform on the segment pin here in blue and the waveform on the COM pin here relative to our circuit ground 0 volts here, this is important, you'll see that they're out of phase because one's the inverse of the other, but they're still 0 to 5 volt TTL CMOS type levels. There's no negative thing involved. But if you look at it from the perspective of the LCD here, if you actually take the difference between these two out of phase signals relative to not circuit ground anymore, because circuit ground doesn't matter. Remember, the LCD only cares about the difference between the common pin and the segment pin. If you take the COM pin as a reference, bingo, it's actually going positive and negative. According to the LCD, as far as it sees it, it's flipping polarity relative to the common pin. So the average value, as far as the LCD is concerned, is 0 relative to the common. There is 0 DC offset, so you aren't violating the issue with driving your LCD by having a DC offset on the common pin, and we're driving this effectively with a single 5 volt, 3.3 volt TTL, the CMOS digital source. Winner, winner, chicken dinner. But I hear you saying, Dave, how do we actually drive this with a real microcontroller or digital logic or whatnot? Where, yeah, you just hardwired this in. Well, we don't have to hardwire these things in. Of course, you could, and if you didn't want your display to change, if you always wanted to display the one thing, you could actually hardwire it like that. Is get rid of our inverter here like this, and if you remember our digital logic fundamentals, which I'll have to link in at the end of this and down below, how can we actually, what sort of gate can we use to control this sort of thing? Aha! That gives us a controlled inversion, your good old XOR exclusive OR gate. So this is your segment in, and this hooks up to here like this. So if you feed a logic 0 here, 0 volts into your XOR gate like this, it's going to work just like a buffer here. It's not going to invert this at all. So your signal here is going to equal your signal here like this. So the segment will be off because there's no difference between the segment and the COM pins. They're not out of phase. We're not driving them out of phase, we're driving them in phase. They're effectively like shorting that pin to that pin. It's exactly the same, but if you put a logic 1 here, bingo, the XOR becomes an inverter and it creates your out of phase signal. Ta-da! We've now got logic control of driving the COM pin like this from a single logic rail circuit, be it a microcontroller, 74 series, 4000 series logic, an Arduino, a micro, whatever it is, you can drive it with a single logic just by doing out of phase waveforms. Awesome! And of course you would do that for as many segments as you have in there. You just need those controlled XOR gates in there, or if you're driving this from a microcontroller, for example, an intelligent logic device, you would just hook these straight up to the pins and then you could generate the required in-phase and out-of-phase signals directly on your microcontroller pins. You just have to be careful. If you had a lot of segments here and they were hooked up to different ports on your microcontroller, for example, there might be a small delay time if you change one port and then change the other, but micros are so fast relative to the quite low, 100 hertz update rate that it really is not going to affect the DC offset thing at all, really. So it's just of academic interest. So there you have it. It's that easy. Just drive them out of phase. I know this might be a bit, it might sound a bit hard. Let's go to the bench, demonstrate the thing. All right, let's give this a whirl. I've got a 74HC86 classic exclusive OR gate here, and you can follow the wiring playing along at home if you want. But what I've got here is this powered from 5 volts, and the gate on pins 1, 2, and 3 here is just a driver for the common pin. I've got the second pin there just strapped over to ground there, so it's just acting as a buffer, and I'm also feeding that same 100 hertz signal on pin number 1 there over to the second exclusive OR gate on pins 4, 5, and 6 there, and the output of that actually driving a segment on the LCD. And I've got it powered up. We've got 5 volts. We're feeding in our 100 hertz square wave. There it is, and you'll see that the signal on both pins there are in phase. So the top one is the common one, the yellow, and the green one down there is the segment. And check out the weird effect when I put my hand, I'm just capacitively coupling my hand, which is picking up all sorts of common mode noise and crap. Anyway, if you hook it up to a 1 there, it inverts the phase, segment turns on, you connect it to ground, there's no inversion in the phase, it's the same signal, the pins are effectively tied together, segment turns off. That's it. That's how you properly drive a static LCD with a TTL signal. The different signal that we actually saw on the whiteboard there, we can actually subtract channel 1 from channel 2. We've got the operator as negative, so we're getting the difference between 1 and 2 here, and we're at a 5 volt per division scale. There is no segment turned on because the waveforms are in phase, so there's no difference signal. There's 0 volts difference, 0 volt offset or difference between the segment and the common. But if we strap that pin over to positive there, bingo, the 0 signal, the ground effectively, as far as the LCD is concerned, is smack in the middle there. And it actually goes up by 5 volts and down by 5 volts. So it's actually 10 volts total. So you actually get a greater voltage to drive it. So if you've got an LCD that needs a higher voltage than other ones, a drive signal, this is a neat way to get both that 10 volt peak to peak from a 5 volt logic level. So if you used a 3.3 volt logic circuit, you would actually get a 6.6 volt peak to peak signal, which will drive practically any LCD at a very large contrast. No worries whatsoever. And if you're wondering how to do this with a microcontroller, or in this case, an Arduino, I've got an Arduino Uno tied onto the back of this thing. We're counting from 0 to 10. That's it. And you'll notice that there's no driving circuitry whatsoever. We've just hooked the LCD directly on to the pins of the micro here. So the common goes to a pin. They're all on the same port, which means you can just switch them all at once. It's easy. And but you don't have to do that. And you could do this with as many pins as you wanted with a static LCD. And that's all there is to it. And we just drive the pins in phase or out of phase like we did before. And for those playing along at home, here's the firmware. David wrote it. While I edited the video, I was going to do it, but I just got him to hack it together in a couple of minutes, and there it is. And there's the Bitwise exclusive OR operator. There it is. Byte port val. It basically just inverts it or not. A controlled inversion for each particular segment that's on. That's all there is to it. Easy peasy lemon squeezy. So there you go. Don't be afraid to either design your own LCD, as we're going to see in future videos in this series, or use an off-the-shelf one and drive it with your either Digital Logic microcontroller or whatever. They're pretty easy to do, at least the static drive version. The multiplexed one will have to require a separate video. Once you go to multiplex, you can do it with a microcontroller and discrete logic, but it just gets a bit harder because you have different bias levels and things like that. And in that case, for multiplex ones, I'd recommend going to a proper LCD driver chip or a microcontroller that has a proper LCD driver built in. So anyway, if you like that video, please give it a big thumbs up. And as always, discuss down below, and there's end card video thingies at the end where you can watch more videos. I highly recommend you do. So yeah, stick around. There will be future episodes in this series where we design a custom LCD. Anyway, hope you liked it. Catch you next time.